Okay, so we all have that image, right? The apple, the tree, Isaac Newton. It's sort of the ultimate science story.
It really is that simple falling apple supposedly sparking this huge leap in understanding.
Exactly. And today, in this deep dive, we're looking at how Newton and then later Albert Einstein completely changed how we think about gravity, the universe itself, really.
And why both of their ideas are still so incredibly important even now.
So Newton comes along, sees the apple, or so the story goes, and develops his law of universal gravitation. What was the core idea there?
Well, the idea was pretty revolutionary for its time. Basically that every single object with mass exerts a pull on every other object.
Everything pulling everything else.
Right. And the strength of that pull depends on, well, how massive the objects are, more mass, more pull, and how far apart they are.
And it gets weaker with distance.
Yeah, much weaker. It fades off quickly, sort of like how light from a candle dims the further you move away.
Yeah.
He put it into a precise mathematical formula.
And this wasn't just theory, was it? This model was powerful.
Oh, incredibly. For more than 200 years, Newton's law was it.
Right.
It was the foundation. It could predict the paths of planets with amazing accuracy, explain the tides, even figure out where a cannonball would land.
So in his universe, space and time were like a fixed backdrop, unchanging.
Exactly. Absolute space, absolute time, a static stage. And gravity was this invisible force acting instantly across any distance. Seemed like the final word, really.
Okay, so Newton's physics ruled for centuries. But eventually some cracks started to show, little things that didn't quite fit.
That's right. By the turn of the 20th century, a couple of persistent puzzles emerged. One was Mercury's orbit.
Ah, yes, the wobble.
Yeah, just a tiny discrepancy, about 43 arcseconds per century, but it was real. And Newton's equations just couldn't explain it fully. It was always slightly off.
And there was something else too, wasn't there? Something about light.
Right. The very strange discovery that the speed of light in a vacuum is constant. Always the same speed, no matter if you're moving towards the light source or away from it.
Which sounds counterintuitive.
It totally flew in the face of classical Newtonian physics. It just didn't make sense according to the old rules. These were the clues that maybe the picture wasn't complete.
And this is where Albert Einstein enters the scene. He tackled these problems head on.
He did. First was special relativity in 1905, which dealt with that constant speed of light and showed space and time are, well, relative, not absolute. They can stretch and shrink.
Mind-bending stuff already. But then came general relativity about 10 years later.
Yes, and that was his new theory of gravity. And it was even more radical.
So what was this completely different way of looking at gravity?
His huge insight was that gravity isn't a force in the way Newton thought. It's actually a consequence of the curvature, or warping, of space-time itself.
Space-time. So space and time woven together.
Exactly. Imagine space-time as a flexible sheet, like a trampoline. If you put a heavy object like a bowling ball onto it, it creates a dip, a curve.
Okay.
Now, if you roll a marble nearby, it doesn't get pulled by the bowling ball directly. It just follows the curve in the trampoline fabric caused by the ball.
So planets orbiting the sun are just following the curves in space-time created by the sun's mass.
That's the idea. Mass and energy tell space-time how to curve, and the curvature of space-time tells mass and energy how to move. No invisible, instantaneous force needed.
Wow. Okay, that is a fundamentally different picture. But how did he, prove it? How do you test something like warped space-time?
Well, that's the beauty of it. His theory made specific, testable predictions. For one, his equations perfectly predicted that tiny wobble in Mercury's orbit. Nailed it.
The exact amount.
The exact amount that had puzzled astronomers. And then came the really dramatic proof during a solar eclipse in 1919.
Ah, the starlight bending experiment.
Precisely. His theory predicted that light from distant stars passing close to the sun should bend because the sun's mass warps space-time around it. Astronomers observed it just as he calculated.
And Newton's theory had no explanation for light bending like that.
None at all. It was a stunning confirmation. Seeing starlight actually follow the curves of space-time.
It's amazing how practical this seemingly abstract idea is today. Like, we actually use Einstein's gravity in daily life.
We absolutely do, even if you don't realize it.
Yeah.
Your phone's GPS is a perfect example.
How so?
Well, the GPS satellites are orbiting way up high, where Earth's gravity is weaker, and they're moving fast. According to Einstein, this means their clocks tick slightly faster than clocks down here on Earth.
Faster? Because of weaker gravity and higher speed?
Yes, it's called relativistic time dilation. It's a tiny difference, mere microseconds per day. But if the GPS system didn't constantly correct for it, based on Einstein's equations,
It would work.
your navigation would drift off by several kilometers every single day. It would be completely useless. So yeah, we rely on Einstein every time we use GPS.
What about really extreme places like black holes?
Well, Newton's laws just completely break down. They can't describe the insane warping of space and time near a black hole. Only general relativity works in those extreme environments. It describes how time can practically stop and even light can't escape.
So wrapping this up then, it sounds like Newton gave us the first incredibly useful map of gravity.
Absolutely, the foundational understanding. Essential for so much engineering and even getting rockets to the moon.
And Einstein came along and gave us a much deeper, more accurate map, showing the underlying landscape of space-time itself.
Exactly. He didn't so much prove Newton wrong, but showed his theory was an approximation, a really, really good one under normal conditions, but not the whole story. They're like sequential chapters in our understanding.
Yeah, that makes sense. And it's important to remember we still use Newton all the time.
Oh, constantly. For building bridges, designing cars, calculating trajectories for spacecraft within the solar system, for almost everything in our everyday experience. Newton's laws are fantastically accurate and much simpler to use. Einstein is crucial for high precision or extreme gravity.
It's quite a journey, isn't it? From thinking about a falling apple to understanding that the fabric of reality itself can bend and warp.
It really is a testament to human curiosity and ingenuity.
Makes you wonder what other things we currently think of as fundamental, as absolute truths, might just be waiting for the next Einstein to show us a deeper level, something to think about.